Hey everybody, welcome back here today. We're going to talk about two topics: determining limits using algebraic manipulations, and then selecting procedures for determining limits. Mostly just the first one though, determining limits using algebraic manipulation. Okay, so a couple basic rules to start out with today. We have a basic limit rules. If we're trying to find the limit as x approaches c of just a constant b. If you think about that, what that graph would be, that would just be a horizontal line, y equals b. Okay, so no matter what x value we pick, we're going to get the same y value back, b. So the limit as x approaches c of any constant b is always b. The second one here, limit as x approaches c of x, that's just a line y equals x. So whatever x value we put in, we'll get the same y value back. So if we put c in, we would get c back. And that's true for just any power of x, not just the first power of x, but any power of x. Okay? Let's take a look at a couple of these pretty basic ones here. The first thing we're going to look at is the limit as x approaches 3 of the number 5. Again, that's just the graph of the line y equals 5. No matter what x we pick, the height of that graph is going to be the same. It's going to be 5. So the limit as x approaches 3 of 5 is 5. Okay, the second one, we have the limit as x approaches 2 of 4x squared plus 3. So if we think of this as 4x squared separated from 3, we can put that 2 in for x in the 4x squared part, and then we also have this plus 3. So that would give us 4 times 4, which is 16, plus 3, and our limit must be 19. Now that process is called direct substitution because we are substituting directly into the expression. Same thing for example 3. We're going to directly substitute 1 in 4x, and we get 1 squared plus 1 plus 4 over 1 plus 1, which is 6 over 2, so our limit must be 3. Finally, example 4, if we substitute pi in for x, we get sine pi over 2. We remember from the unit circle that would be 1. So our limit as x approaches pi over 2 of sine of x is 1. All right, what if we have a function, but we can't directly substitute in? Okay, that's what we're going to look at here on these next 4 problems. Let c be a real number and let f of x equal g of x for all x except for c in the open interval containing c. Then the limit of as x approaches c of f and the limit as x approaches c of g would be the same. What does that mean? Example 5, what you want to try to do right away is put negative 3 into this problem. We would get 9 minus 3 minus 6 over negative 3 plus 3. And if you simplify that, you get 0 over 0, which is good news and bad news at the same time. The bad news meaning you got to do a bit more work. But the good news is that the limit does exist. Okay? If we got 0 over any other number but 0, so let's say, for example, we got 0 over 7, okay, that answer would just be 0. Conversely, if we got any number besides 0 over 0, so maybe 7 over 0, that means the limit does not exist. Okay, but in this special case, where we get 0 over 0, that means there's a hole in the graph. And we've talked about this before. Okay, limits are about the journey, not the destination. So we're not trying to find out whether or not there is a hole in the graph. That doesn't matter. All that matters is that we're trying to reach that hole in the graph. I know it's not going to reach it there, but that's okay. It tries its best. Okay? So how do we figure out what that is? What we're going to do is some algebra. We are going to factor the numerator and denominator if we can. Now in this case, we can only factor the numerator. Okay, this is the same problem, except we just factor the numerator. And now if we cancel, that's why this is called a factor and cancel problem. We factored it, and then we canceled it, and now we have this. Okay, what this up here is saying is that this function and this function are the same function everywhere except at -3, at x equals -3. The only difference is at x equals -3, this one has a hole. This one does not. So wherever the y value is for this one, that is where the hole in this one would be, and therefore that is where our limit would be. So now we can substitute -3 in here, and we get our limit must be -5. So what does that mean? That means that on the graph of this function, there's going to be a hole at -3, -5. Here's another example. You want to try to put 1 in there right away, but you're going to get 1 minus 1 over 1 minus 1, which is, again, 0 over 0. Okay, and that should immediately tell you that the limit does exist. And we got to find it. So we can try to factor limit as x approaches 1. This is a special difference of cubes formula that you should hopefully know from your previous math classes. It factors to a minus b times a squared plus ab plus b squared. All over our denominator, x minus 1. And now we can cancel these two out. And we're left with this expression, which we can now substitute 1 in, and we get 1 plus 1 plus 1, which is, of course, 3. So our limit is 3. And what does that mean? That on this graph, there's a point 1, 3. It's a hole in the graph. Next one's called a conjugate problem. What does that mean? Well, it's important for us to know what a conjugate is. First of all, a conjugate, if you have a plus b, the conjugate of that is a minus b. So those are called conjugates. Okay? So we want to start by putting 0 in. Unfortunately, you're going to get root 1 minus 1 over 0, which is, of course, 0 over 0. So again, that tells us the limit does exist. So how do we find it? For problems such as this, you're going to multiply by the conjugate of, in this case, the numerator over itself. Okay, why is that allowed? Because really, we're just multiplying by 1. We're not changing the problem at all. We're changing how it looks, but it's not going to change the overall problem. So we get limit as x approaches 0. Root x plus 1 times root x plus 1 is just x plus 1. The middle two terms will cancel because this is going to be a difference of squares, and then -1 times +1 is -1. And that's all over x times root x plus 1 plus 1. Do not distribute the denominator. You'll see why soon. Simplifying the numerator, we just get x over this whole denominator. And that's why you don't want to distribute, because now we can cancel x over x. And that leaves me with limit as x approaches 0 of 1 over root x plus 1 plus 1. And now we can put 0 in. We get 1 over root 1 plus 1, which is 1 over 2, and that's our final answer. So our final answer here is the limit as x approaches 0 of root x plus 1 minus 1 over x equals 1 over 2. Example 8 here, we're going to call this a fraction action problem because there's a lot of fractions and there's going to be a lot of action. Again, you want to start by putting 0 in for x, but once again, you're going to end up with 0 over 0, which tells you the limit does exist. Okay, there's a hole in the graph, but the limit exists. So what we're going to start by doing is getting a common denominator up here. So the common denominator is going to be 3 times x plus 3. So we have limit as x goes to 0. Multiply this by 3 over 3. Multiply this by x plus 3 over x plus 3. And we're left with 3 minus x plus 3 over 3 times x plus 3 over x. And I'm going to put that x over 1. So remember to flip and multiply here in the next step. Okay, so now we have a limit as x approaches 0 of 3 minus x minus 3 over 3 times x plus 3 times 1 over x. And that gives me limit as x approaches 0 of negative x over 3 times x plus 3 times 1 over x. These x's can now cancel. And I'm left with limit as x approaches 0 of negative 1 over 3 times x plus 3. Now we can put 0 in finally. We get negative 1 over 3 times 3. So our final answer for a limit as x approaches 0 of 1 over x plus 3 minus 1/3 over x will be negative 1/9. All right, here's something you may have done in your calculus or your pre-calculus class. This is actually what we're trying to do here is find the limit definition of a derivative of a function. Okay, and if you try to do this, obviously if you put 0 in for h, you're going to end up with 0 over 0. All right, so there's a lot of work to be done, but nothing we can't do. Limit as h approaches 0 of 4 times x squared plus 2xh plus h squared. Distribute that negative 3. So minus 3x minus 3h plus 2 minus 4x squared plus 3x minus 2 all over h. Distribute this 4. I'm left with limit as h approaches 0 of 4x squared plus 2xh, plus 8xh plus 4h squared, and I'm just going to copy all this down again. And now we can cancel some things. 4x squared and minus 4x squared will cancel out. Negative 3x and positive 3x will cancel out. 2 minus 2 will cancel out. And I'm left with limit as h approaches 0 of just these 3 terms, which you can see all of an h in them. So if I factor an h out, I'm left with 8x plus 4h minus 3 all over h. Why would I want to factor those out? Because now I can cancel this h, and now I have limit as h approaches 0 of 8x plus 4h minus 3. And now I can put 0 in for h, and that gives me 8x plus 0 minus 3. So we'll learn this in the future here, but that's going to be the derivative of the function we were originally working with that we put into this difference quotient to start, 8x minus 3. All right, lastly is piecewise functions. So be careful with these. If this number is anything but where this splits, then you just have to put that number into which expression it belongs in. So for example, if I change this 2 to a 3, since 3 is bigger than 2, I would put 3 in here. If I change that 2 to a negative 2, Since that's less than 2, I would put that negative 2 in here. But unfortunately for us, we're looking at 2. And 2 is where this function is split. So what we got to do is we got to do a left-hand, right-hand limit and see if they match. So limit as x approaches 2 from the left of f of x. So which one is the left? This one is less than 2, so that's going to be from the left. So if we put 2 in there, we get 5 times 2 plus 2, which is 12. Now we got to look at the right-hand limit. The limit as x approaches 2 from the right of f of x. That means that this one is to the right, because that's greater than 2. We put 2 in there, we get 3 times 4 minus 1, which is 12 minus 1, or 11. Since 12 and 11 are not the same, that means that this limit does not exist. So limit as x approaches 2 of the function does not exist. If it was any number but 2, it would exist. But at 2, it does not. There must be a jump in the graph at that point. Okay? That will do it for today's lesson. Thanks for checking in, and we'll see you next time.